Okay, so what we're going to do next is to implement the model that we created for problem 5.2, the shortest path problem in last week, into Excel. So please go to your Moodle site, go to the current week, which is week 6, and download this week 6 chapter 5 data. Okay. And in this file, I've already included all the required data here to save some time for you. Okay, and the model that we're going to implement is this 5.2, the shortest path problem. Okay, I've already converted that network into this table format representing all the possible paths, the from node and the to node. Also put the driving time here and the scenic writing time here. Okay, node number and the corresponding city name are given here too. And before we go to implement this, let me introduce a very useful Excel formula to you, which is the Vlookup formula. Okay, which I put it here in problem 5.1. So what this Vlookup function does is that it searches in a certain table. In this case, this table here, for a specific value included in this cell here. Okay, so it look up this value that's contained in cell C6 in this table here. And if a match happens, it returns the value in the corresponding, in the matching row, and in the second here. This is a 2, so it in the second column. For example, look at in this table here for this value 1, and when a match happens here, that's the matching row. It returns the value that's in the matching row and in the second column here. Okay, so if for example this table here, if we enlarge it, then we would need to change this column number to 3 to let it return. So let's add something. Oh, sorry. Go back. For example, if I insert a column here, okay, just suppose I insert the column here, see here, then it will still look at this matching row, and now it will return the value in the third column in the matching row. So now it still returns this value here, this new work. Okay. So why this VLOOKUP is useful is because we only have to put the code and the city number, which is kind of like index table once here, okay, without typing, without the need to type those city names every time when we have a node. Okay, so that's the VLOOKUP function. So what we're going to do is let's copy this table here to a new sheet. That's the problem, the 5.2 that we're going to implement. And then I'll ask you to put the city name for all the node number, correspond to all those node number. Okay, for example here, node 1 means that's Birmingham. So what you want to do is to use that index, the VLOOKUP function. So equals VLOOKUP. And first is ask for the lookup value. So which value you're going to look up. And I'll put here. So we're looking up this value 1 in the table array, which will be this table here. And if a match happens, return the value in the second column. Okay, so I'll put 2. And of course, this 2 here can be referring to a cell that contains a value being 2. Okay, or you can just put this value 2 here. And I like to have this formula, this formula copied all the way down here, and also to this 2 nodes here. So I'm just going to fix this entire index table here. So let's use put the function f, function 4, okay, to put $sign before the row number and the column number. Oh, what did I do? So I'll put the function 4 here. Okay. Okay, so that's the Vlookup function that we're going to put here. So Vlookup this value, and in this index table, which get fixed by putting $signs before the row and the column numbers. And if a match happens, return the value in the second column. Okay. Now I can just copy this function all the way down. And you can check. So okay, this is node 10, and it returns ready. So that's good. Then next thing I'm going to do is just to copy the function, paste it here. Okay. And since we fixed this table, you can see you click in it, and we look up this value and in this table. If a match happens, return the second column. Okay. Copy it all the way down. Okay. And put this border back. Okay, so that's the Vlookup function. Next, let's use this column here, shade them yellow to represent to save the reserve the space for our decision variables. Okay, remember our decision variables are whether to take a specific route or not. So here there will be 0 1s. Okay, representing whether to take the route from node to the 2 nodes. Okay, so I'll say choose the route. 1 means yes, 0 means no. Okay. And so we have the decision variables place specified. Okay. The next thing to do will be to calculate the objective function. Objective function in this problem can be two things. Okay. First is the shortest driving time. Second is highest scenic rating, or just calculate them differently, separately. So here I'll calculate the total driving time. Okay, and total driving time is the sum product of my decision variables and the driving time column. Okay, because we know that eventually those decision variables value will be 0 or 1. So if it's a 0, then the driving time, meaning the route is not chosen, and the driving time will not be included in the total driving time. If it's 1, that means we're going to take that route. Then the driving time of that route will be included in your total driving time. Okay, I'll shade this in blue, representing that's my decision objective function. Okay, we'll just do the driving time now. And what we need to do next will be to specify the constraints. Okay, and remember, for this network problem, the constraints are inflows minus outflows equals to supply or demand in this problem. Okay, because we assume we have one supply and one demand, so supply equals to demand. Therefore, our constraint will take the format being inflows minus outflows equals to the supply or demand. And so to calculate the left-hand side of your constraint, that would be the inflows minus outflows. So here I'll separate the inflows in one column and the outflows in another column. Later, when you get very familiar with these formulas here, then you can just have one column being the net flow. Okay, but in this first problem, we'll separate them here. We'll have inflows, outflows, and net flows. Okay, to calculate the inflows, I'm going to introduce another very useful formula, which is the sum if formula. Okay, let me just first put some value here to illustrate. So I'll just put tens here. And this, what does this what does this function that I'm going to introduce does is that the name is sum if. Okay. What it does is that it look at a range and compare that range to a value, which is this criteria part. And if a match happens, then it will take the sum of another range in the matching row. Okay, for example, I'll say sum, look at a range. Okay, say there's a from range. Okay, look at this range, compare the values in this range to my node value here. Okay, if a match happens, then return the value, the sum of the values in the matching rows here. Okay, for example, let me use this 6 instead of 1. Okay, so what I'm doing now is that, okay, I'm going to look in this entire range to see if there is any value that's the same with this one, which is 6. And if there are any value that matches this 6 value here, I'm going to take the sum of the value in this range in the matching rows. For example, in this case, we have how many 6? 1 here, right? Another 6 here. Okay, so we found the two matches, and what the formula does is it will take the sum of these two values. Okay, so what it did is that it looked at this range to compare the values in this range to value contained in this cell here, and when it found a match, for example here a 6 and another 6, it takes the sum of this third range here in the matching rows. Okay, which means this 20 comes from these two 10 numbers. Okay, so it's the sum of this and this. And why this formula is very useful is because when we try to calculate the inflows to a node, we can first, let me ask you, how do you know, for example, these are all the decision variables, right? And these decision variables represent the flows from a certain node to a certain node. And how do we determine which values are the inflows to a certain node? And how do we determine which those values, among those values, which ones are the outflows from a certain node, say node 6. Okay, let's just look at node 6. Which ones are the inflows to node 6? And which ones are the outflows from node 6? Think about this. Or think in a way that when you calculate the inflows for node 6, How do you write that? Write that constraint. You always write, okay, the inflows would be x something, right? The first subscript we don't know. Just based on here we can see, but we know the second subscript, so will be xi and 6, right? The first subscript we don't know which are they. We need to look, but we do know if a value here is a inflow to node 6, then the second subscript must be 6. It need to be flow into node 6. So then let's see, okay, which ones are the inflows? We have 2 here, right? And another one here. Okay, do we have more? No. Okay, so these 1, 2, 3. These 3 flows are inflows to node 6 because they represent the flows from a certain node to node 6. Okay, and if it's outflow from 6, then we look at the from node. Okay, we don't care whether it's going to node 8 or 9 or 10 or 11, but as long as that for this flow it has a from nodes that start from this 6, then these two represent that's an outflow from node 6. Okay, so with that we can use the SUMIF function here. Okay, here what we're going to try to determine is the inflows to node 1. Okay, in this case we know there is no inflows to node 1 because node 1 is a starting point. It's a supply node. However, we still need to write a function that can be copied all the way down for all the nodes. So the function needs to be general enough. Okay, so what we're going to do will be we use the SUMIF function. Okay, I'll modify this. Okay, we'll look at the range because this is the inflow range. So we look at the to range. Okay, we look at the to range, and if we see node 1 there, that means the corresponding decision variable represents a inflow to this node 1. And to sum up all the inflows, we'll sum all the corresponding rows in this decision variable range. Okay, and we want to copy this formula all the way down so that every time we look at the inflows for a certain node, it will just compare this node number to numbers in this to range, and if it found a matching number, then it will sum the decision variable value in this corresponding matching rows in this table here. Okay, so we want to fix this. I'll put function f4. Okay, so you can see that inflows to node 1 is 0, which is right. And we'll copy it all the way down here. Okay, click inside this. Okay, now we see for node 6, the inflows, it will look at, okay, in this range, which ones are node 6? We have 1, 2, 3 here. And then we sum this value, and this value here. That gives us 30. So we have inflows to node 6 is 30. Using those numbers we put. Okay, so these are the inflows, and as we said, if we want to calculate the outflows from the node, then instead of looking at this to range, we will look at this from range now. Okay, so we'll use SUMIF. We'll look at the from range, and to see if any value in this from range is the same as our node number. If it's the same, that means the corresponding decision variable in that matching row represents a outflow from this node. Okay, for example, in this case, node 1, we see 2 of them, right? So this 10 and this 10 here represent the outflow from our node 1. Okay, and then sum if so now that if a match happens between this node number here and the from node, will sum the corresponding row in this decision variable part. Okay, and again we want to fix the ranges, so we'll put $sign here so that we can drag this all the way down here. Okay, so we have the inflow, outflow, then the net flow will be very easy, equals to be inflows minus the outflows. And we'll copy this all the way down. Now we get our net flows, which is the left hand side of our constraint. And the right hand side would be supply or demand. And the supply demand, we know that we have one supply at node 1. We represent it using negative value. 0 for all the transshipment nodes. And 1 at the demand node, which is the destination part. Okay. Then we can go to the solver window to define. Our objective is to minimize the total driving time. Okay. And our variables are those yellow shaded ones. Okay. And our constraints will just be the net flows. Inflow minus outflows equals to be supply or demand for each node. Okay. And make all the variables non-negative. Choose the algorithm and solve. Solver find the solution. All constraints and opportunity conditions are satisfied. Okay, that means we find the solution. Okay, good. So you can see that we're going to go from node 1 to 2, and then from 2 to 4, and from 4 to 7, from 7 to 10, and then 10 to 11, with the total driving time being 11.5. Okay, so this is the way that we formulated this shortest path problem, and this is the way that all the transshipment problems are formulated. And we're going to have more exercise next week. Okay.